All right, welcome back. Our next lesson in our discussion of probability distribution functions is going to involve the normal distribution. I'm excited about this one because for years we've heard about, the classic bell curve, especially in like school and stuff, how teachers graded on the curve, or they created, created a bell curve for their grades that they wanted to give on a test or something like that. And so now we're going to actually be able to explain and put that terminology into an equation form. Now, I'm going to admit the equation is rather ugly. You can see it on the page already, and it's a little icky to work with mathematically using what we learned in the last video, but I'm going to show you a shortcut methodology that makes these problems super easy, okay? But the normal distribution is one of the most important distributions in all of engineering, right? It shows up everywhere, and in fact, we have little shortcuts that we can do for even when the distribution isn't normal, things that I can do to let us approximate it as normal, okay? And we'll get into some of those when we get into the central limit theorem and start talking about probability and statistics in that regards a little bit later on in our series. But for now, the normal, or what is sometimes called as the Gaussian distribution, is critical to everything that we want to do. All right, so we're going to kind of set this up the same way that we've done the other videos, and then we're going to kind of walk through some of the methodology and show you some of the tricks and the properties that we have. All right, so we're going to set up our random variable x. Okay, we're going to say that it is normally distributed and it requires two parameters. It requires mu and it requires sigma squared. Okay, so you notice it needs the population mean and it needs the population variance. Okay, so we must have the parameters for those. Now, that can be a problem when I get into statistics, where if I get into an immeasurable source, that I can't possibly get the population data, what do you do? And so that would be some of the issues that we'll face that we have to kind of work on to get clarified. But for this video, for now, we're going to say, okay, we'll accept that and we'll keep on moving on, okay? But again, these are two population parameters that we're looking at. So if I do that, then the normal distribution for a random variable x having parameters of mu and sigma is given by the following equation. And then, like I say, it's a little bit ugly. It's 1 over what is the square root of 2 pi, okay, and then multiplied by a sigma outside of the radical, okay, and then that quantity gets multiplied by e raised to this really screwy exponent, okay, and it's minus x minus mu quantity squared all over 2 sigma squared. Okay, and so you can kind of look at it and you can kind of see there's kind of a variance thing kind of hiding in here. X minus mu squared, you've seen that behavior before back, when we were talking about variance, but that's the form of the Gaussian, right? So if I plug in my value of x, this thing will spit out a probability for that value of x, okay, that this will evaluate down. Now again, the range of x is from minus infinity to positive infinity, all right? So it is fully defined even at, you could be working on a normal distribution on a 0 to 100 scale, but technically, according to the math, there is a probability I could get a score of 1,000,000 on a test. Okay, practical limits. There will be some things that we do to kind of solve that problem. But mathematically, it says it's possible. It'll be a real small probability, but it is possible. Okay, now the good news is that our expected value and our variance for the normal distribution are very easy to compute because you already have them. All right, so the expected value of x is the mean, or this population average, and the variance of x is just simply sigma squared. Okay, so you will know those up front, okay, and then we can fit our data. Now, again, this curve represents kind of a bell-shaped function, and that it is, it's mounted in the middle. It's centered, the peak point here is centered at our expected value mu, and then our curve is f of x. Looks like this, and it goes all the way from minus infinity all the way up to positive infinity is our normal bell-shaped curve. All right, so now, if we tried to calculate probability, say between a lower bound A and an upper bound B, like we did in the last lessons on this, and try to compute this average that was living in here between those two limits, that integral would get really ugly really fast. I mean, look at it. It'd be an e to the x squared. So anytime you have an exponent, it's not bad. But if you start putting an x squared in the exponent, now you've got integration by parts and a whole bunch of other things that have to happen, from a mathematical standpoint. So as engineers, we like to do things a little bit better because that's just not real fun to do. All right, so that's what we're going to try to do, is come up with a better way. And so this better way that we're going to come up with is kind of a numerical integration technique. Okay, but we're going to start off and we're going to define a special class of probability distributions. In this case, we're going to define the standard normal. Okay, and what this is basically a basis distribution that we can serve, that we can use as a reference for all other normally distributed distributions. Okay, again, we're still bounded by those rules for creating a valid PDF, and so this, depending on X and mu, may or may not be a valid PDF. There are still some rules that have to happen. So what we're going to do is we're going to force the rules. Okay, and so we're going to define a new random variable that we're going to call a z. This is kind of the classic value that's used, and this is what our book uses as well. We're going to say that z is normally distributed on the interval of 0 and 1. Okay, now if we follow this, by that logic, we're saying that our population mean is 0 and our population variance is 1. Okay, and so then by plugging these values into our basic Gaussian definition up here, okay, this thing greatly simplifies down. It becomes 1 over square root of 2 pi times e to the minus z squared over 2 as the exponent. Okay, so that's a whole lot friendlier to work with, and in some calculus tables we could go pull this value out. Okay, but the interval on z is still from minus infinity to positive infinity. It's a lot nicer to work with. Okay, so that's going to kind of form our basis for what we're going to do. All right, now once I do that, okay, we can start looking at extending this and saying, okay, well, for the standard normal, and we'll come back around to getting this to work for non-standard ones, but just so you kind of see the process, is we can define our CDF. This is our cumulative distribution function, and they use this phi value here, if you will, and then as a function of z is going to be equal to then the probability that my z characteristic is less than or equal to some little z. And if you remember, when we did this operation, it was always the integral from my variable to minus infinity of the function definition, in this case the f of y on 0, 1 dy. Okay, and so again, it's not real nice to integrate, but you could do it to build the CDF. What a lot of statistics books do is they tabulate these values for you, and in fact they've done that in our textbook as well. Okay, and I'll show you here in just a second a little bit of that. But so what they've done is they've basically said, all right, well, it's a cumulative function, so if this is my normal curve, and I know that I'm centered at 0 because that was the requirement that we had on our normal distribution, that it was 0 here and a 1 variance on this thing. Then this phi of z value, if I locate z, say it's over here to the left somewhere, if I locate that z, then this phi of z represents the area of everything to the left of it. So this is the CDF area. And so this is what we're going to try to look at as we start to tabulate this. Now let me pause the video and I'm going to get the book open so we can study the effects of this table. Okay, so here's what they've done, and it's basically the same as the picture that I drew for you. This is table A3, located back in the appendix of it. And so what they've done is they've represented this shaded area. Okay, and they're saying then that this phi value, this phi of z, is equal to then the probability of my z random variable being less than some numerical value. And I'll show you how to come up with what that value is that correlates us back when we start doing non-standard normals. So this is what we call a standard normal density curve. This is the density function, the PDF, if you will. All right, and so this shaded area is phi of z. Now, one thing to note on these is this book chooses to do it as a CDF. I have seen sources where instead of doing less than z, they do greater than z. Okay, and sometimes that calculation makes sense in its applications, but you got to make sure that what you're pulling out of these tables represents, and there's got to be a picture somewhere that shows you what it is that these values represent. All right, and so the way that it works out is that this is my z value that I'm looking for. So suppose I'm looking for, minus 3.05. Well, I'm going to come down to minus 3 and then come across to the hundredths at 0.05, and so that value would be right here, that probability to the left of minus 3.05 becomes 0.0011. It's a very, very small, it's like 0.1%. So I mean, you would be way out here on the end at that value. And you'll notice that, in the book that there are two sets of tables. There's the negative page, which we have here, and then the next page over has the other half of it, and it goes from 0 all the way up. Okay, so what happens is the standard normal curve, you'll look at the smallest value that we have then is minus 3.400. Anything outside of that, you notice that at this very smallest value, we're at 0.0003. All right, I mean, that's what, 3/10,000ths. It's basically nothing. So if you ended up with searching for a value that's less than this number, the probability is 0. And all of a sudden, you now have a test for outliers. Okay, that if I'm beyond this, that could be a way to assume that, okay, there's something wrong with the data point that I've been given. And likewise, on the other end, you'll notice that this curve is symmetrical, right? It's a bell-shaped centered at 0. So whatever's happening on this side is matched by what's happening on that side. So over on the positive tables, if you look, you can see that the uppermost value then is 3.4, and then this is 3.49, gets me that value. Okay, and so that's minus 0.9998. Okay, and I guess I misspoke. Up here, the minimum value is this 0.002. It's the minus 3.49, so I apologize for that. Okay, so that's my minimum value. But you notice that that value and that value are complements of each other, right? Because this is everything to the left. So at this point, I'm now basically 100%. To the left of that value. And so if you go anywhere beyond that, now it's basically a 0% that occurs outside of that range as well. So all of those become kind of some techniques for being able to read this. The table is really easy to use otherwise. All right, so we'll get that book out of the way and we'll kind of get ourselves back to what it is that we're trying to do. All right, so let's take a look at this. Okay, so that's kind of where we're going with being able to use these tables. So, on a quiz or a test, obviously you'll have access to these tables, but those tables are very useful just in practice anyway, anytime you try to do a probability of a normal distribution. All right, so we've defined our basic Gaussian, and we've defined the standard normal, which have characteristics, but what do we do when it's not standard? Okay, and so this is what we're going to do, is we're going to basically come up with an idea that I can take any normal distribution and I can transform it back to one of these. Okay, and if I do that transformation, then we can use the standard normal tables in all circumstances. And so I'm going to show you what we're going to do. All right, so here's what we're going to do. Let's define my random variable x as being normally distributed with mu and sigma squared. Okay, we're going to define a z parameter, the value of z then, as being simply x minus mu divided by sigma. Okay, and so then what happens is that the probability of x being less than some value of a is now going to be equal to the standard normal area of a minus the population mean over the population standard deviation. Okay, and so what happens when I do this is that I've made the shift from here, which was non-standard normal, and turned it into a problem that is a standard normal. If I could spell it right, that would help. All right, and that's the power of what we've done. We've done this mapping, if you will, to get from one to the other. And then once I get my value here, then the probability of this is the exact same probability as this. Okay, all because of the way that we've set up the PDFs as we start to do it. So that's where we're going with this. Okay, so that's how we're going to handle. So it's all comes down to this little box here. This shift is everything that we're going to do to be able to use the standard normal tables. Okay, so let's try one. I've got an actual problem to work on here. Okay, and so we're going to look at, this one is a tree diameter study. Okay, somebody's gone out in the woods and measured a bunch of trees and plotted the data and concluded that it is normally distributed. Okay, so they're going to define their random variable x as being the measured tree diameter over here. Okay, and so measurements in a forest are made. From the data, it is found that x is normally distributed of mu, of a population mean and a variance, if you will, where mu is measured, the population average is 8.8 inches, and the standard deviation is 2.8 inches. Okay, all right, so those are some parameters that would come out of a set of data that has been collected or measured from somewhere. All right, so once I have that, now we can start asking questions. Find the probability from this section of the woods that a random measurement is greater than 10 inches. So if we write that, that's a probability that my random variable x is greater than 10. Okay, now if you notice, again, this goes from positive infinity to negative infinity is the range on a normal distribution. So I would be going from 10 all the way out to positive infinity, or I could choose to go, since normal distributions of these measurements, obviously I can't have a negative number on a tree diameter, right? It'd be some sort of like black hole kind of thing happening there, right? It's a negative area. Doesn't work, all right? So we're bounded by diameters, the minimum value being 0. So for this problem, it makes sense to use the complement and flip it. So instead of looking for x greater than 10, I'm going to do 1 minus the probability that x is less than 10. Now, again, I don't care whether it's less than or equal. That equal sign doesn't matter on this because of our singular values that we talked about in the last video. But I do know that this guy here is now the CDF, okay, because it's a left-bound CDF. And if it's a CDF, I can use the standard normal tables if I make that shift. All right, so all we have to do is define our random variable z as simply being x minus mu over sigma. So I'm looking for the value of 10. My mu is 8.8 and my sigma is 2.8. My z value is 0.429. Okay, and so what we're going to do is we're going to call that basically 0.43, right? Because again, our tables only have 2 decimal places. So to calculate this, then the probability of x greater than or equal to 10 is going to be 1 minus the probability of x less than 10, which is the same as 1 minus the probability of z less than 0.429, and now he's a standard normal. All right, and so what we've done is it's 1 minus p and then z less than or 0.43, and so that's all I've done. I've done the shift. I've gone from an x into my new random variable that I've defined as this function, and we're off to the races. All right, so you can go in, and we kind of did this already, but just so you have it written down, the procedure is we go into the table and we read off. So the first number we're going to look for is 0.4. That's the first part of this z value that we have. And then I'm going to read off the rest of it, which is 0.03 gets me out to here. That's the portion here. And basically where those two intersect is the number I'm looking for. And if you do this, you can check it for yourselves, that this value is now 0.6664. Okay, is the probability of being less than that z value of 0.43 on a standard normal curve. Okay, and so when I do that, then you'll notice then I can plug that value in over here. So 1 minus that value, because again, we did the complement. Okay, and so probability that x is greater than or equal to 10 then is 0.3336. That's all there is to it. The hardest part of this whole thing was coming up with that transformation. Okay, and that part never changes. You just plug in your x, you have your population mean, your population standard deviation, and away you go. The problem arises when I don't have these guys. What do I do? Okay, and so there will be some rules that we'll cover for how do we handle those type of problems in another video. But for now, we'll assume that we have it. We'll play the game the way they want us to play it. Okay, all right, now, recognize that, again, we kind of talked about this, that the probability that x is greater than or equal to 10 mathematically is the same thing as the probability of x greater than 10 plus the probability of x equal to 10. And you'll remember that we said these singular values on a continuous were always a 0. Okay, and so and we talked about that in the last video as well for continuous distribution. So I can shift freely between greater than or equal to and greater than, and it's the same value, and I can move back and forth on those. All right, so that's kind of how we do the first step. Okay, now let's go through and let's try another one. Okay, let's try what's the probability that the diameter exceeds 20 inches. Okay, so now we're getting a little bigger on this thing. All right, so all I do is I play the same game. Probability of x greater than 20. I flip it, 1 minus p, probability of x less than or equal to 20. And then I convert from my x to my z. And so my z on this should be because I'm looking for 20 now, 20 minus mu over sigma. Okay, and if I plug all this math in, this z value from this operation ends up being 4.0. All right, and so 1 minus the probability of z less than 4.0. Okay, on the table that we had in the appendix that I just showed you, the maximum for that value of z was always 3.4, right? And it had a probability of around 0.9997. Okay. And we showed you those values in the tables earlier. Actually, I think it was 0.9998, but we're so far down in the decimals here, it doesn't make a lot of difference for us at this point. So what that means is that it being at 4.0, a positive 4.0, again, that's a positive value right there. Being at positive 4.0 basically tells me that that's basically 1.0. So if I take and do my complement 1 minus 1.0, this says the probability of finding a tree x greater than 20 is basically 0. Okay. If you were asked to solve that problem, you would say there's something not right. That just, statistically speaking, that's not likely to happen. Okay, now there may be some other reasons why it's there. Maybe somebody came in and planted a tree with 20, or it was missed in the original measurements, or whatever the case may be. It's not actually 0, but it's very, very, very small. It's highly unlikely. And so that's kind of the start of our outlier testing that we can start to do. Okay, all right. The next one then is let's look to see what do we do to find the probability my diameter is between 5 and 10 inches. Get units on there. Okay, and so probability of 5 less than x less than 10. All we're going to do is come in and take the probability, the cumulative of the upper bound, and then subtract off the cumulative of the lower bound. So probability of x less than 10 minus probability of x less than 5. Again, if you don't understand this, go back to the previous video on continuous distributions, and we'll talk about where those areas are coming. Okay, and so now we have the probability of z less than or equal to 10 minus mu over sigma minus probability of z less than 5 minus mu over sigma. I plug in my mu and sigma values, and so now I'm doing statistics for a z of 0.429 and doing a z of negative 1.357. So the negative basically tells you you're to the left of the mean of 8.8, which obviously 5 is less than 8.8. Okay, so if you're to the right of it, it's positive. If you're to the left of it, it's negative. It all works the exact same way. So I'm going to round that to minus 1.36. And so you can go look at the tables. We have this value from before, 0.6664. And then so that's this one, and this is that one. Okay, and so if I look this value up in the table, I get minus 0.0869. And then I do the math. My probability of being in that range is 58%, or 0.580. So pretty simple to be able to set all these up. So this ability to be able to break pieces and go into, sums of cumulatives is very, very important in this normal distribution discussion. All right, now the last one that I have is a little bit of a different animal, and this is kind of a sneak peek, if you will, for some stuff that we're going to do later on in statistics called intervals. Okay, and so we're going to find a value of c such that the probability of my mean, my mu minus c less than x less than mu plus c, okay, is equal to 0.98. Okay, so if you think about this in terms of what it's saying, is it's saying that I want to take my mean of my standard distribution and subtract a number from it such that when I subtract a number from it and then add a number from it, the area between those two lines is 0.98. Okay, this is the beginnings of something called a confidence interval, all right, in which I can start predicting data, with some degree of certainty. So in this case, this is a 98% confidence interval, if you want. Okay, and so what we're going to do is we're going to kind of play the same basic game, but now I've got this unknown c. But what I do know is that if I do my standard normal curve, we're looking to go from positive z to minus z such that the phi value is 0.98. Okay, that's all we're doing because the areas have to match, right, when we do our mapping. And so if I do the algebra, that's all I'm doing here is I'm going to start off with my x variable, 0.98 equals probability of x less than 8.8 plus c minus probability of x less than 8.8 minus c. So that gets me the two limits. Okay, and then I shift from x to my z variable. And when I do that, then the point that we're looking for then ends up being c over 2.8, and then it's c over 2.8 on the negative side over here. Okay, and so all of that's going to add up to be 98%. Now, the one trick in this, when you start playing with these ranges, is we have to take advantage of symmetry. All right, so the fact that I have this area being the same as this area, what I can do is I can come in and say, well, this is going to be 2 times the shaded area minus 1 will get me the exact same expression. And what I've done is I've now eliminated the c from 2 locations and put it into 1 here. So we've taken advantage of symmetry and then played some games by subtracting the 1 on this. So when I bring the 1 to the other side, that's 1.98. I bring the 2 over, divide by 2. That gets me 0.99. And so basically this is everything from here to the left as I start to do that, okay? And so then the probability of z being less than c over 2.8, I can now back my way out of the math on this thing. All right, so the z value is 2.33. You'll see this number over and over on confidence intervals. Okay, and then from that, I can say c over 2. I can convert it back and find out that c is going to be 6.5 inches. So if I take my value, I go 6.5 off of this, that goes to 2.3, and 6.5 on top of it goes to 15.3. That 98% of all the data points in my forest are going to fall between those two limits. Okay, so that's a way that you can kind of work this range into it with some degree of certainty. And so if you're in manufacturing or something and you're doing normally distributed operations, this gives you a way to start being able to measure quality or certainty or those kind of things. And it's a very, very powerful concept, being able to set these widths, if you will, that get me a certain level of tolerance or a certain level of, quality, if you will, as we start to kind of look at that. So that's one of the things that we can look at on that as well. Okay, all right. Now, the last problem I'm going to show you is it's still the tree problem, but it's a little bit different. All right, so let's look at what do we do if, say we go into the woods and we select 4 trees at random, what is the probability that at least one exceeds 10 inches? Okay, so this kind of combines not only the normal distribution, which was what my data was built off of, but now we're going back to probability and playing with our event constructors. And I want to kind of highlight how you solve this, or how you start to think about this problem. And it's actually a lot easier than you think. So what we're going to do is we're going to define an event, AI, being the scenario where we find a tree with a random variable x on that measurement being greater than 10. So basically that the ith tree is larger than 10 inches. That will be my event. We've done this calculation. The probability of xi being greater than 10, we said, was 0.336. We did that one from before. Okay, but the question becomes, how do I do it when now all of a sudden I'm wanting to know, what's the probability that if I select 4 trees, that one, at least one, so it's an at least and one exceeds that. Okay, so what I do on this one, and again, this one's simple enough, but I can draw a Venn diagram just to kind of get my head wrapped around what is it that we're trying to draw. And so I have 4 events that all overlap, and you can see it gets rather complex. And so like this point is the point where all 4 of them exceed 10 inches. And this point would be where only A exceeds. This is only C exceeds. This is only B exceeds, and so on. And you can go, oh, that's A and B, but not the others. And you can build this construction based off of our Venn diagram scenario. Go back and look at the Venn diagram video that we did a little bit earlier if you're not understanding this. But pictorially, what we're looking for is, if we read the problem, we're looking for the probability of at least one exceeding 10 inches. So if we look at our diagram, that if this is event A exceeds, this is event C exceeds, and B and D, then every point that's shaded inside of here satisfies that criteria of at least one. I didn't say exactly one, because exactly one is here and here and here and here. Okay, and I didn't say 4 because that's here, and I didn't say 3, that would be these guys, and 2 would be these guys. At least one covers all of this. So it's all of this shaded region. Right now, if you look at this, what this shaded region represents is we want at least one exceeds. Well, that's the union of all 4 of these events. Okay, so A, union B, union C, union D would be that event, right? Now, again, we don't know how to calculate it, but we know that that's kind of the relationship. Okay, the region that's outside of this then would be the none exceeds case. Okay, it would be the complement of this thing. Okay, and so the complement is actually the intersection of the complement of A, complement of B, complement of C, and complement of D. That all 4 of these have to occur. We say intersection is the both event, but it's all of them occur at the same time, in which I get the complement of each of the values that we found before. Okay, and so if that's the complement if that can be defined as the intersection of the complements of the individual events, then this is the complement of this. All right, and so the complement of my empty box, the outside region on my sample space, is the same. Complement of that is the same as my shaded region. Okay, all right. So if we look at this, then what we're going to do is we can assume that A, B, C, and D are independent events. Okay, that they're just random trees, random samples. There is no premeditation. And if we take advantage of independence, then I can calculate that the probability of A intersect B intersect C intersect D would be the probability of A times probability of B times probability of C times the probability of D, right? And so if we go through and we do that, then the event that we have for the probability that all 4 of them are happening is going to be equal to then the probability of a single one, which we called out as a single one exceeding 10, 0.3336. Okay, and so that probability is now 0.336 raised to the 4th power. Okay, and that numerical quantity is 0.1972. And then we can say then that the union that we defined, that shaded region, was the same as 1 minus the complement of the complement, basically. And so we can find out that at least one exceeds 10 inches at a probability of 0.8028. Now, like I say, you could go in and you could do tree diagrams if you wanted, but this guy is 4 levels deep. It gets pretty ugly in trying to find all of the outcomes that go with that. This and this and this and this and this. And if this is, and then you add another branch on that, if this is a knot, there's only one outcome down here that we're after. Okay, in order to be able to find the complement, we're trying to find the sums of all of the others. Okay, so again, you can kind of pick your battles on how you want to approach it, but I wanted to show this one because this kind of shows how I can take the methodologies that we're learning with normal distributions and finding probabilities of a single random variable, but I can still bind them together in interesting ways that I ask bigger questions. All right, the probability that at least 1 exceeds 10 inches. Well, I needed the probability that 1 exceeded 10 inches, which is what we've been doing with the purpose of this video. But now I can go in and I can start chaining these things together using Venn diagrams or, or probability trees or any number of techniques. But it's kind of, I thought it was kind of an interesting problem to start to kind of look at it. So anyway, I hope that made sense to you. I hope it shows you some of the power of what it is that we can do with our normal distributions. So we'll stop our discussion there on the normal distribution. Like I say, it's just more of the same. It's just a continuous distribution. But now we've got tabularized integrals, if you will, of that standard normal. And you make that one little shift on the z coordinate, and then everything else is done exactly the same way. So like I say, I hope this made sense to you. As always, toss us a comment down below if there's something that you don't understand or something we need to clarify, and we'll do that. No problem. Please like the video. That'll help us out a bunch. And then, as always, subscribe to the channel. And with that, we'll wish you a fond farewell. Have a great evening, and we will talk to you next time. Happy engineering.